I have about 10 slides on the problem of Bell's inequality and Bell correlation and the status of Bell correlation in algebraic quantity theory. I'd like to be quick so that we have time for the next lecture as well. But it's an important and interesting issue. And here is the main definition with which we can start, namely the definition of Bell correlation between two commuting von Neumann subalgebras of the von Neumann algebra in a particular state. It's the supremum of this correlation here. The supremum is taken over all self-adjoint operators here with norm less than or equal to 1. This definition is irrespective, or it is outside of quantity theory. It makes sense for general von Neumann algebras. And this is the kind of correlation which we will investigate in the context of quantity theory, where these von Neumann algebras will be local von Neumann algebras in a net, and the interesting case is, of course, when they will be von Neumann algebras associated with regions which are space-like separated. But before turning to that, a couple of general statements about the Bell correlation. Summers and Werner have shown that there's an a priori bound on this Bell correlation, which is the square root of 2 in the category of C star and von Neumann algebras. And then once you have this definition of Bell correlation, you can define Bell's inequality as this inequality, namely when the Bell correlation is less than or equal to 1. This notion has a history which I won't go into. If you know a little bit the history of the problem of hidden variables and Bell's work, then you recognize immediately that this Bell correlation is defined on the basis of some developments in connection with Bell's inequality, which I assume to be familiar for everyone. Now, another definition here, which is very natural then, if this is Bell's inequality, is the notion of Bell correlated state. The state is called Bell correlated if this Bell correlation is strictly greater than 1. And you say that the state is such that it violates Bell's inequality maximally if it is equal to its maximum value, which, as I said, was the square root of 2. A state is called a product state across these two sub-von Neumann algebras if the value of the state on two observables, on the product of two observables from the respective subalgebras, factorizes the product of the expectation values of the observables. Now, here is a proposition which characterizes the classical situation. Namely, if the two von Neumann algebras are such that any of them is commutative, or if it is the case that the state is a product state across these two von Neumann algebras, then the Bell correlation is equal to 1. It's another way of saying that is that the state satisfies Bell's inequality in this case. Again, there are two such typical cases: when the state is a product state across the algebras, or when any of the algebras is commutative. Any of them commutative is enough. On the other hand, if we are in the truly quantum case, namely if none of them is commutative, then Bell's inequality is violated. The more precise statement is here. It was proved by Werner and Summers in 1986. If you assume that the two von Neumann algebras are acting on a Hilbert space and they have the Schlieder property, then if none of them is commutative, then there exists a normal state which violates Bell's inequality maximally. Here's the definition of the Schlieder property. It's an independent property. It says that the product of the two observables x and y is not equal to 0 if none of them is equal to 0 and when they are from the respective von Neumann algebras. So what this means that in the typical quantum case, when neither of the observable algebras are commutative, then there will always be states that violate Bell's inequality maximally, no matter what kind of phenomenal algebras you're dealing with. So this already entails violation of Bell's inequality in quantum theory, as I'm sure you anticipate, because if you have a net and if you have two phenomenal algebras associated with space-like separated space notations, they are not commutative. The CCR algebra is not commutative. Then there will be states across these space-like separated local observables which violate Bell's inequality maximally. So this result already entails the violation, which is stated here on this next slide for completeness. But if the phenomenal algebras are type 3, and if you remember in one of the previous slides I claimed that it's a major result of the algebraic approach, that the local algebras are type 3, at least in some cases under certain conditions which are typically satisfied, then this violation of the Bell inequality is far more dramatic. Here's a proposition which was proved by Clifton and Halverson in 2010. If you have two commuting type 3 phenomenal algebras which are assumed to be acting on a Hilbert space, and they have the Schroeder property, then the set of unit vectors in the Hilbert space, which induce Bell-correlated states on the two phenomenal algebras, is open and dense in Hilbert space norm in the unit sphere of H. That is to say, there's an awful lot of states which violate Bell's inequality maximally if the algebras are type 3. And since the local algebras in quantum theory are type 3, the Bell inequality is violated far more dramatically than in the general case, and in the type 1 case in particular. Here are propositions specified in the context of the algebraic quantum theory about the status of the Bell's inequality, Bell correlation in that theory. Here are the precise statements then. So we assume that there is a net having the standard features, then the following two propositions are true. If you have two arbitrary space-like separated double cones, then the associated phenomenal algebras are type 3 and have the Schroeder property. So in that case, there is a dense set of unit vectors that define that Bell-correlated states on these two. On the other hand, or even more dramatic is the violation, if these two space-like separated regions are tangent double cones or complementary edges, then the Bell's inequality is maximally violated in all normal states, also in the vacuum state. Okay. So again, here's the situation. If you have two space-like separated space-time regions, of which you only know that they are space-like separated, but you don't know more about them, then there's a dense set of states, dense set of normal states, which violate Bell's inequality maximally. And if these two regions are such that they are tangent double cones or wedges, which are situated like this. This is the tangent cone. This is a double cone. This is a double cone. And I explained here that a double cone is an open region. Okay. And two are space-like separated and tangent. If their closures intersect at one point, at this point, then they are called tangent double cones. In that case, Bell's inequality is violated maximally in all normal states, including the vacuum state. This is a particular situation, and the other situation is the wedges. This is the right wedge. This is the left wedge. These are the light cones. This is the left wedge. This is an unbounded region. This is the right wedge. This is an unbounded region. And then also, if they are in this situation, tangent, then Bell's inequality is violated maximally. Now, these statements are very characteristic of quantum field theory because they don't have any counterpart in ordinary non-relativistic quantum mechanics, where you always find states in which Bell's inequality is not violated. You do find on the tensor product states. There are there, and they, as the product states, satisfy Bell's inequality. But in the quantum field theory case, this is not what happens. Then, if you have the tangent situation, then all normal states violate Bell's inequality. Now, what is interesting here in this situation is the following. So the vacuum violates Bell's inequality for tangent space-like separated regions, and for any space-like separated regions, there is a dense set of normal states violating Bell's inequality. These are the previous two statements. Yet, it is not known if the vacuum state is in that dense set. That is to say, it is not known still today if the vacuum violates Bell's inequality for non-tangent space-time regions. It is one of the intriguing open questions here. I myself have tried to prove something about this, and I know that Ichiro, Professor Kitajima, also has been struggling with this for a while. I don't know for how long you have tried to prove something in that connection. I have tried for about 4 months intensely. I failed miserably, and no one has been able to show that the vacuum does violate Bell's inequality on strictly space-like separated algebras. Although I think, at least I do, I think many who have followed these developments think that what one should try to prove that the vacuum does violate Bell's inequality in that case. Of course, it is always a big question what you try to show, but I think in this case, this is what people have tried to show. In fact, I know that the Hans Salversson and Clifton's result, which I recalled a couple of minutes ago, was the result of their effort to prove that the vacuum violates Bell's inequality. They also failed, but they have been able to come up with this statement. Okay? So this is one of the open questions which you might want to work on, although it might not be advisable if you are a PhD student who is supposed to have some result and submit his PhD work within a reasonable time to start working on this, because it seems to be extremely difficult and you might not be able to prove something on. Okay, some further comments on the violation of Bell's inequality. If you have two arbitrary space-like separated, possibly tangent double cones, then the associated von Neumann algebras are both C star and W star independent, or statistically independent. This issue came up already in a little discussion with Professor Ozawa, and I'm going to talk about these independence properties tomorrow. But here we need the definition of C star and W star independence just to make a point. So I'm recalling here the definition of C star independence and W star independence. Two von Neumann algebras are C star independent if any two states, phi1 and phi2, on the respective algebras NV1 and NV2, have a joint extension into a state on the generated von Neumann algebra. And they are called W star independent if any two normal states, phi1 and phi2, on the respective subalgebras, have a joint extension to a normal state on the generated algebra. Now, it is also known that in the case of C star independence, there exist joint extensions which are product states across the two algebras. Okay? Note that I did not say that the extension is normal. I didn't say that, but there exist extensions which are product states. The point here is the following then concerning the Bell's inequality situation, is that if you are in the tangent regions, which are space-like, tangent but space-like, then you have the following situation. Any two normal states, because of the W star independence of these algebras, any two normal states have a joint normal extension W star independence and A star. Okay. But that normal extension cannot be in a product state, because if it were, then it would satisfy Bell's inequality, but it doesn't, because all normal states violate. On the other hand, any two states have a joint product extension, none of which can be normal. It's curious, it's strange. This is a very, very crazy situation, okay? You have two regions, tangent double cross, okay? And the following is the truth. No matter how you give me two normal states, I can extend it to a normal state to the generated algebra, but that extension cannot be normal. I'm sorry, I can extend it to a normal state, but the extension cannot be a product state. Okay. On the other hand, no matter how you give me two states, I can have an extension which is the product state, but that cannot be normal. Okay. A very curious situation. I'm not quite sure what to say or think about this. This is why I put this question. Is there something to be explained here? This shows a strange behavior, a very subtle distinction between normal and non-normal states, okay, in relation to this tangent situation. Okay, these were the couple of slides which are left over from the previous talk, so let me just summarize this lecture here. I claim that algebraic quantum field theory is a quantum theory that incorporates the ideas of locality and relativistic causality using the mathematical machinery of C-star and W-star algebras. And the theory is specified axiomatically, and the axioms have a number of mathematically both deep and physically, philosophically intriguing, I claim, consequences. What were these? Well, one was that the notion of particle as a strictly localized entity, localized in bounded space-time regions, is not a maintainable position, it's not a maintainable concept. That was the consequence of Redei theorem. And the other was what I had just discussed, namely that the Bell's inequality is violated in that theory, and that implies that there's correlation between observables which are localized in space-like separated space-time regions. And it is important to realize that to date there is no model of the axioms in four-dimensional space-time that could be interpreted as describing interacting fields. So that's perhaps the compact summary of lecture number 3, I'm sorry. So let's go to number 4, lecture number 4. Yes, this is it. And this is devoted to the topic of causal completeness of quantum field theory. To be more precise, devoted to the status of the so-called common cause principle of quantum field theory. So here's the outline of what I tried to do in the somewhat truncated time in 1 hour. I have to be fast. I might skip a couple of things in order to fit everything in. First, I will talk about the common cause principle in general, the common cause principle and the causal completeness notion. I will define a notion which is due to Reichenbach's notion of common cause in classical probability spaces first, and I present a couple of propositions in this classical context. They are interesting in their own right, quite independent of quantum field theory, and there are open questions there which you might want to know about. And then I return to the notion of causal completeness, the notion of common cause, and the causal completeness notion related to that in a non-classical probability framework. Again, that's still not within the framework of quantum field theory as such, but it will be, of course, related to quantum field theory because that's a non-commutative probability theory, as I claimed in my second talk. Then I will raise the issue of causal completeness of quantum field theory in the general sense. We will define the notion of common cause, which is local in quantum field theory, and then I present you a proposition which is not satisfactory, but that's the only thing which we know at this point, namely that weak inversion of the common cause principle can be proved to hold in quantum field theory. And then there are some very recent results about the status of the common cause principle in lattice quantum field theory in 2 dimensions, and I'd like to show you what these results are. Namely, the weak common cause principle, which holds in the full 4-dimensional non-discrete case, can be shown to be violated in the discrete case. On the other hand, there's a modification of the notion of common cause, bringing up certain features of the common cause in a non-commutative context, which saves the common cause principle in the sense that one can show that the weak inversion holds in the lattice quantum field theory in 2 dimensions. So that's the outline. And here is first the notion of common cause principle. This principle goes back to Reichenbach. Remember Reichenbach, I mentioned his name and his views in my first lecture. He's a major figure in history of philosophy of science, and he formulated this principle, compact version of which is the following: there's no correlation without causation. Explicitly, this means that if you have 2 events which are probabilistically correlated, then either it is the case that there is a causal connection between the 2 correlated entities that is responsible for the correlation and explains it, or if this is not the case, it can be excluded, then there is a third something, a Reichenbachian common cause, which brings about the correlation and explains it. Okay. So this is a metaphysical principle, a philosophical principle somehow, which is a claim about the causal structure of the world, and it says that if you see correlation, and you do see correlation in the world many times, then there are only 2 ways the world can be. One way the world can be is that the correlated entities are somehow correlated because they are causally related, or if this is not the case, then there is something which is in the history of both of these, in the past history of these correlated entities, which is responsible for the correlation. Okay? Now this principle, like any philosophical principle, has been very extensively discussed in the philosophy of science literature. Is this true? Is it not true? Is it reasonable? Is it not reasonable? And the general consensus is that this principle is threatened essentially by quantum correlations in the quantum world. The quantum type of correlations, the EPR correlations, and specifically the correlations which quantum field theory predicts are such that they don't have a causal explanation. So the whole research, which we also have done, and some of you also, is related to this issue. Is it true that the common cause principle really is violated? It's not by quantum theory, that it is not valid in quantum theory. That's the background of the whole issue. Now, let's assume that the principle is valid. Then it's a very natural question to ask whether our theories are causally complete, can comply with this principle in the sense of being causally complete by providing that causal explanation which the principle says should be there, either in terms of a causal connection or in terms of a common cause. And the main message of this talk or this lecture is that causal completeness of probabilistic theories in general is a non-trivial feature, but it is possible to have it. And the causal completeness of the particular theory we are talking about in the algebraic quantum field theory is essentially an open problem. Okay? We don't really know what the situation is. I think the situation is, again, very intriguing. I have more to say about this in the end, what possible positions one can take in connection with this issue in light of the available results and in the light of the efforts which have been devoted to this problem. Okay, so let's go into the details. That's the main message. The main message being, again, that we don't know what the situation is, and certainly quantum field theory cannot be considered as a theory that provides evidence against the common cause principle, not at this point. Here's the definition of a common cause, which is at the heart of this whole issue. Namely, if you have a classical probability space and you have a correlation in it, then between two events A and B, then a third event is a common cause of the correlation if it satisfies these four independent conditions. What are these conditions? Well, the correlation disappears in the probability measure, which is the probability measure obtained from the original one by conditionalizing on the common cause. Because here this means that these two events, A and B, are probabilistically independent with respect to the conditional probability measure, conditioned by C. The same is true for the probability measure, which is conditioned by the orthogonal component of C, the common cause. And the probability of A happening on condition that the common cause is present is strictly greater than the probability of A happening on condition that the common cause is absent. And similarly for B. These two conditions are called the statistical relevance conditions. The common cause is statistically positively relevant for A and B to happen. And these are called the screening of conditions. This condition is sometimes expressed by saying that the common cause screens off the correlation between A and B, and similarly, the absence of the common cause screens off the correlation. Now, you might want to ask, why this definition? What's the rationale behind it? There is a rationale behind it which I'm not able to detail here. There are intuitively appealing examples of situations, classical examples, in which an explanation of the common cause along these lines seems to be intuitively attractive. Okay? I'm not giving you, I don't have time to give you examples, but if you have a look at Reichenbach's book, The Direction of Time, which was published in 1957 after he died, you find examples there which illustrate the reasonableness of that definition. So I just take it now, formally, that's the definition, formally it's a precise definition, and the question is then whether our theories are probabilistically complete in the sense of containing common causes of the correlations they predict. That's the issue. Okay. Now, the definition of causal completeness. Remember what the notion of common cause principle was. It said that if there is correlation, then either there is a causal connection, or if there is no causal connection between them, then they're supposed to be explained. The correlation is supposed to be explained by a common cause. And the causal completeness definition expresses that. Suppose you have a causal independence relation on the set of random events, then as probability theory is said to satisfy the common cause principle if it is causally complete in the sense that it contains a common cause of every correlation which is between causally independent events. Seems reasonable, right? So a probability theory is causally complete if it can give you a common cause explanation of every correlation which is between causally independent events, because of the correlations between causally dependent events, if there is such a correlation, are explained by the causal dependence. Okay, so that's the definition, and then the problem is, under what conditions is a probability theory causally closed? There's a lot of room here to play with, and this notion can be developed in many ways. And you realize also that one can make a probability space causally complete in a cheap way, namely just by defining the causal independence relation in a particular way so that it makes the probability space causally complete. Namely, you just define A and B causally related, that is to say, you say that the causal independence condition does not hold whenever A and B are correlated, but there's no common cause in the space of the correlation. But of course, this is not what you
are interested in this cheap way of making theories causally complete for a number of reasons. You need a disciplined definition of causal independence. Again, I said there's a lot of room to play here with it. So a lot depends on how you define the causal independence relation. And a very weak condition of the causal independence notion is the following intuition, that if A and B are causally independent, then you should be in the position that you are not able to infer either the occurrence or non-occurrence of B from the absence or presence of A. And conversely, from the presence or absence of B, you should not be able to infer the occurrence or non-occurrence of A. This seems to be a minimal condition. Otherwise, you would not claim that the two events A and B are causally independent. Now, two events in a Boolean algebra are logically independent if these conditions hold. That's more or less standard definition. A doesn't entail B, not A doesn't entail B, A doesn't entail not B, not A doesn't entail not B, and so on. None of these, all of these are independent somehow. And two sub-Boolean algebras of the Boolean algebra are called logically independent if any two elements in them, which are not trivial, which are not contradictions, are logically independent. Another way of expressing this feature is to say that two sub-Boolean algebras are logically independent if no matter how you take one proposition from one and another from the other, the two can be jointly true in some interpretation. That's the content of logical independence of two sub-Boolean analyses. And then it's a very natural definition to say that the probability space is causally closed with respect to logically independent sub-Boolean analysis if it contains a common cause of every correlation between those elements which belong to these logically independent sub-Boolean analyses. So we have now a more specific notion of causal completeness, of causal closeness, which intuitively is, I think, defensible. And the question is, which spaces are causally closed in that sense, and which spaces are not? What can we say about this? And the first proposition which I can present you here is that a finite probability space is not causally closed with respect to every pair of logically independent Boolean subalgebras. Again, if you have a model of your verb, your physical situation, which is such that the probabilistic model is finite in the sense of the Boolean algebra being finite, as a finite cardinality, finite number of elements, then that probability theory is not causally closed with respect to every logically independent Boolean sublattice. Okay? There's a small print here. Curiously, there is one exception, which, however, I don't know what to do with. The Boolean algebra, which is generated by 4 atoms with a uniform probability measure on it, is causally closed with respect to all Boolean subalgebras, which are logically independent. But that just seems to be a coincidence, a mathematical coincidence, and I don't think it has any philosophical or physical or whatever significance. So this was proved in 2004 in this little paper in Foundations of Physics by a student of mine and myself. We published this score. His name is B. Janish. B is in red. I'm working with his brother as well, who's a mathematician, with Zola and Janish. And so I have drawn a whole family into this business, unfortunately for them. So this is why this B is in red. Another proposition which is true is that in every finite probability, there exist logically independent Boolean subalgebras with respect to which the space is causally closed. So it cannot be closed with respect to all logically independent sublattices, but there are sublattices with respect to which it is causally closed. Another proposition here is that if you have a finite probability space which is causally not closed, which is typically the case with respect to a pair of Boolean sublattices which are logically independent, then that space can be extended in such a way that the extension is finite and is causally closed with respect to the logically independent pair consisting of the homomorphic images of S1 and S2. So suppose you have a probability space which is causally not closed, containing a correlation between two elements which are causally, logically independent, and there is no correlation, or no common cause for them. It's a very natural idea to ask then, can it be the case that this probability theory is embedded into a larger one, such that the larger one already has that common cause of the correlation? By a larger one means a space with a Boolean algebra and a measure on it, such that there is the Boolean algebra embedding of the small space into the large one, which preserves the probabilities. Okay? It's a very natural definition of extension. And the claim here is that indeed this can be done. So any small space can be extended into a larger one, which is still finite, such that the larger one has an explanation of the correlation in terms of the common cause. The philosophical motivation behind it, or physical motivation, you don't have to call it philosophical, is that maybe your probabilistic model, which predicts a correlation but is not able to explain them, is just too small. You have not taken into account enough parameters, enough events in the world, and if you had done that, maybe your theory, your richer theory, would be rich enough to give an explanation of the correlation. It's a very natural idea to ask whether this is possible, and the claim here is, yes, this is possible, which is a kind of consolation, if you believe that the common cause principle is a valid principle. But even if you don't, this has heuristic consequences, heuristic value, because it tells you, look, you have designed this probability space to describe a certain phenomenon. This probability theory gives you a correlation, but you are unable to explain within that theory the explanation. Maybe you should have another theory, which is a better one, a larger one, richer one, finer one, which is capable of giving you an explanation of that correlation. And this proposition says that indeed this thinking is a good thinking because it's maintainable mathematically speaking. The next issue, okay, so far at the previous slide contained propositions about finite probability spaces. The finite probability spaces are discrete in some sense. They are the opposite of what monatomic probability spaces are. Non-atomic probability spaces, non-atomic in the sense of measure theory, are the following ones. A probability space is purely non-atomic if the following is true. For any A which has a non-zero probability, there exists another event which is smaller, which had a smaller probability, strictly smaller. So no matter how you choose an element in that probability space which has a finite, a non-zero probability, there will be an event in that probability space which has smaller probability. Okay? There is no smaller probability event in that probability space. Okay? And if this is true, then this space is called non-atomic in the measure theoretic sense. Notice that non-atomicity can also be defined for the algebra itself, and non-atomicity in the measure theoretic sense and non-atomicity in the algebraic sense are different concepts, although they are not independent, they are not unrelated as we will see, but they are conceptually different. Here's an example. The normalized Lebesgue measure on the 0-1 interval is purely non-atomic as measure space, but the Lebesgue measure of the sets form an atomic Boolean algebra because the one element sets, which are closed sets, are in the Lebesgue measure of the sets. Okay, so it's atomic as a Boolean algebra, but the measure space is non-atomic. a relative definition is the measure theory atom, a p atom. An element is a p atom if it has non-zero probability, and for all elements which are smaller, we have that the probability of that element is equal to zero, or the probability of the element itself. Okay. Why is the issue of non-atomicity and atomicity relevant? Well, anticipating what's coming, because these are the opposites for the finite probability space. And indeed, somehow, it turns out that non-atomic probability spaces are better behaving from the perspective of the common cause principle. Namely, what turns out is that non-atomic probability spaces will be common cause complete. What I mean by common cause completeness is the following, that any correlation in them, no matter what, no matter between where the correlated events belong to or not, they will have a common cause. The correlation will have a common cause. To be a bit more formal, if the causal independence relation holds for all correlated events in that space, and the space is causally closed with respect to that relation, then I call it common cause complete. So if this holds for all correlated pairs in the space, then causal closeness with respect to that thing is called common cause completeness. And here's a proposition about non-atomicity. This shows why the non-atomicity is relevant. That if you have a non-atomic probability space, then it is common cause complete. So in non-atomic probability spaces, we are all right. They are extremely rich in events, so rich that every correlation has an explanation in them in terms of the common cause. Now, this points to the general problem of the role of non-atomicity and atomicity in connection with the common cause principle. Because as we have seen, probability spaces with finite Boolean algebras are not purely non-atomic, measured theoretically, and they are not common cause complete. Whereas the purely non-atomic ones are common cause complete. So the question is, what precisely is the role of measured theoretic atomicity in common cause completeness? Clearly, one fears that measured theoretic non-atomicity somehow is directly relevant for common cause closeness. And indeed, that turns out to be the case. Here is the proposition. This is with Zolan Janisch, the brother of the other guy with whom I published that paper. And this is in philosophy of science. The following characterization of common cause completeness can be given. A probability space is common cause complete if and only if it has not more than one p atom. Or putting it differently, a space is common cause incomplete if and only if it has more than one p atom. So we cannot expect, essentially, what this says, that common cause complete spaces are purely non-atomic. This is what essentially is true. So if you have a Boolean algebra which has a finite number of elements, then it's not common cause closed. Finite probability space typically always contains, with the exception of that particular one I mentioned, always has more correlations than it can explain with the help of common causes only. Now, these common cause completeness, closeness result also makes it possible to show something which is a strengthening of the proposition which I stated before, which was that if you have logically non-independent sublattices in a finite Boolean algebra, and it is not common cause complete with respect to that, then you can extend it in such a way that the extension obtains a common cause for that particular correlation. There's a more general, more powerful statement to that effect, and it is the following. Every classical probability measure space is embeddable into a purely non-atomic probability space. And since purely non-atomic probability spaces are common cause completable, every classical probability measure space is common cause completable. The significance of this is that the strategy which I mentioned to you before is a possible strategy, it's a logically possible strategy to defend the common cause principle, namely to say, in view of seeing a common cause incomplete probability space, not that the common cause principle is not true, but that your theory is just too meager. It's a possible strategy to say, in view of a theory which doesn't give you a common cause explanation of a correlation, which it should on the basis of the common cause principle, that the theory is just not rich enough. It doesn't have enough elements to be able to give an explanation in terms of common causes. And if you had a larger theory, then you would be able to explain the common cause principle and thereby to defend the common cause principle. And this proposition shows that indeed this is a possible strategy quite generally. It is always possible to say, logically speaking, that a theory is just too small, too meager. Every theory can be extended in such a way that the extension will be purely non-atomic. And in that space, common causes exist for every correlation. Okay? So purely non-atomic spaces are important because they are just extremely rich. Clearly, a purely non-atomic probability space has to have a continuum number of random events. It's clear from the definition. The cardinality of a purely non-atomic probability space, the cardinality of the Boolean algebra, is at least as large as the continuum. Okay. Further twist on this notion, the notion of common cause completeness and common cause completability can be strengthened. One can define, namely, the type of the common cause in terms of the values of the probabilities which are indicated here. You might want to say, okay, there are different common causes possibly for a correlation, and a particular one can be characterized by fixing these conditional probabilities and the probability of 2. And then you can show that for a correlation typically, in principle, there's a continuum number of these numbers which you can fix and which is allowed in principle for the common cause to satisfy. And then you can call a probability space strongly common cause complete. It contains a common cause of every possible type of every correlation. Clearly a very strong notion. And it's not clear whether this notion is self-contradictory or whether it is maintainable. Questions which are open at this point. Do strongly common cause complete probability spaces exist? And if yes, are probability spaces strongly common cause completable in the sense in which I described? My suspicion is that the purely non-atomic probability spaces are strongly common cause complete. That is to say, they have so many events and probabilities are so fine-tuned that every type of common cause there can be found. But these are open and they are completely well defined. There's a proposition here which I would like to state, namely, it could be proved that every classical probability space is strongly common cause extendable with respect to any finite set of correlations. So if you have a probability space which is common cause incomplete, you can extend it in such a way that you can extend it in the following way. You fix the type of the common cause, and I can give you an extension which contains a common cause of the prescribed type. Okay? This is possible for any finite set of correlations. and I think it's reasonable to conjecture that this proposition holds for a countable infinite set of correlations, but this has not been proved yet. I think it's just a technical raffinery which would be needed here, and I think that should be provable. Okay, so much about the common cause problem in the classical context. This is the origin of the problem of the common cause investigation in the non-classical, non-commutative context. Because of course you can replace the notion of common cause, you can design the notion of common cause in a non-classical probability space. How? Well, you replace the classical probability measure space with a non-classical one, typically by the von Neumann lattice of projections, as replacing the Boolean algebra and taking a normal state. And then you can define the correlation between compatible elements, and then you also can design the analog of the notion of common cause in a non-classical probability space just by taking over Reichenbach's definition without essentially any modification. Namely, if you assume that the common cause, or you require that the common cause of a correlation is supposed to be such that it is compatible with both A and B, which means that they are from the same distributive sublattice, and they satisfies the screening of and the statistical relevance conditions. Recognize that these are just screening of conditions taken over from Reichenbach's definition, and these are the statistical relevance conditions. So this is the definition of common cause in a non-commutative probability space. It is a conservative definition in the sense that C is assumed required to be compatible with both A and B. I come later to the question whether it makes sense to weaken this condition by allowing C to be non-commutative with A and B. And then the notion of notions and problems which have been defined in the classical context can be defined without any modification in this non-classical context, namely the type of the common cause, the logically independent sublattices, the causal incompleteness, completeness, completability, extendability, the strong common cause completability, pure non-atomicity, everything which has been defined in the classical context can be defined without any problem in this non-classical context, and the same type of questions and problems arise, and many are open. There are some results which have been known in connection with this issue. There is a proposition which is due essentially to Ichiro. We improved upon it a little bit, not much, just a little bit. The proposition is that if you have an atomless sigma-complete orthomodular lattice, and phi is a sigma-additive faithful probability measure on the lattice, then that space is purely non-atomic. And if it is non-atomic, then it is common cause complete. And if it has two or more phi atoms, then it is not common cause complete. So quite essentially, the point is that essentially the same is true as what is true for the classical case. Okay. All right. There is also a proposition which is in progress. We are just writing a paper on this, which is also the analog of the classical proposition. Remember that the classical proposition was that every probability space is extendable, embeddable into a purely non-atomic one. And this is also true in the non-classical case. And we think we have shown this, we are just writing up the paper, so this is in progress. So every non-classical probability space can be embedded into a purely non-classical one, which means also that the argument which I specified as a defense, possible defense of the principle of common cause in the classical context can be extended, is valid, can be extended to the non-classical case, is valid for the non-classical case as well. Because purely non-atomic ones are common cause complete. There are problems here which are open. The question is, one question which is open is whether every common cause incomplete non-classical probability space is strongly common cause completable. I suggest that the answer is yes. And also weaker question, whether every common cause incomplete non-classical probability space is strongly common cause extendable. This is weaker than weaker completability, strongly, and I think the answer to that question is yes too, but this has not been proved. These are open questions. Now I'm approaching the issue of the status of the common cause principle in quantum field theory by relating the general statement by Ichiro and ourselves about the non-atomic situation. We know that the type 2 1 and type 3 von Neumann algebras are non-atomic as lattices. The projection lattices of type 2 and type 3 von Neumann algebras are non-atomic. And if you have a faithful measure on them, which are normal, then the probability space, which is defined by this probability, by this faithful normal state, are common cause complete. But there are particular cases of the general proposition. And the significance of this proposition is that, as we have seen in connection with the Bell correlation, quantum field theory does predict correlations between projections that are localized in algebras which are pertaining to space-like separated space dimensions. And since space-like separated space dimensions are causally independent, if you want to explain these correlations in the spirit of the common cause principle, they should be explained and explainable, and the only way to explain them is explain them in terms of some common cause. And this proposition indicates that this should be possible because there's a common cause of this type of correlation. Because the local algebras in quantum field theory, as we have seen, are type 3, and so there are common causes of this correlation. So are we happy about this, or are we not happy? Well, we are a little bit happy because this opens up the possibility of the causal completeness of quantum field theory. On the other hand, we shouldn't be completely happy at this point because if you remember, algebraic quantum field theory is a local quantum field theory. So you would only want to say that it explains the correlation between space-like separated quantities if the common cause which is required for the explanation is localized in a particular, peculiar way. Okay, so the common causes should be not just any projections which we know that such a projection exists, but they should exist in a particular local algebra. Okay, so where should they be localized in the first place? Well, obviously, they should be localized somehow in such a way that they intuitively respectable in the sense of being capable of affecting the correlated entities causally. Now, there are three possible regions of locality which you can think of, and here they are defined formally. But I think I should better draw a picture which makes it more understandable what's going on here in terms of regions. Suppose you have two space-like separated double cones. This will be the typical situation. These will be the local algebras which contain correlated projections. and you draw the backward light cones. Oops, it's not that nice, but it's all right. So where would you like the projection to be? Well, ideally, you would like to have the projection to be localized where? Somewhere where? Where would you like to be? Where would you like it to be localized? Well, in the intersection of the backward light cones of the two regions. Where are they? So that's the backward light cone of this one. That's the backward light cone of this one. So you want it to be somewhere here, right? But you can also define it to be somewhere here. That's a possible region as well. And a possible region also to say that they are somehow in the union of the two backward light cones. So the whole region from here, they're taken out, the two regions taken out of it. Okay? So there are three possible localizability regions. They are defined on the slides, okay, formally. And they have different causality properties, as I say here. This is the strong past, the intersection of all the backward light cones of all the points. If there is something here, then from that point you can reach any point here and there by a time-like curve. Okay? And if you're somewhere here, you can reach at least one point. If you're in the union of the backward light cones, then every point in that can reach at least one point in either here or there. If you're in the intersection of the backward light cones, then it is the case that from any point from there, you can reach one point in both there and here. These are the differences, okay? Clearly they are different in their causal behavior, different in their causal strength, so to say. So these are three possible localizability regions for the common cause. And the question, and ideally what you would like to have is to have a common cause which has the feature that it can reach one point here and one point there. That is to say, the intersection of the backward light cones. That's what you would like, because that's the intuitively attractive position. Namely, there's a correlation here. There's supposed to be something there which should be able to reach both that one and that one. Now, the question is then what the situation is about the localizability. So here's the definition of local common cause. You say that the field theory, the local field theory, satisfies the weak common cause principle, respectively the common cause principle and the strong common cause principle, if it is the situation that for any two regions, V1 and V2, if there is a correlation between the elements A and B that belongs to V, AV1 and AV2, which are space-like, there will be a common cause in an algebra which is located in the weak past, strong past, weak past, common past, and strong past of the two regions. If this is the case, then you say the system satisfies the weak common cause principle, the common cause principle without any adjective, and the strong common cause principle. Okay. That's a crucial definition. That's the heart of the whole matter. Again, you would say that quantum field theory satisfies the common cause principle if it is capable of giving an explanation of these space-like correlation in terms of properly localized common causes. They're properly localized means it's an intersection of the backward light cones, or you say that it weakly satisfies the principle if there is a common cause localized somewhere in the union of the backward light cones of the two regions, and the strong common cause principle if it is localized in the union of all the, if the intersection of the vector light points. Now, the following is true. If you have a quantum field theory which has the standard features, then the local net satisfies the local primitive causality. And if the net satisfies the local primitive causality condition, which I'm going to define on the next slide, then the field theory is weakly causally complete, in the sense of being able to provide an explanation in terms of weakly localized common causes. It's not strongly causally complete, and it's not known if it is causally complete without any adjective, stronger than weak, weaker than strong. So we don't know if properly localized, properly meaning in the intersection of common causes exist. We know that they cannot exist here in the strong common cause, simply because, if you remember, Bell's inequality is violated for complementary wedges, and for wedges, the strong common past is empty, so there's simply no room for any common cause to be localized in that region, so it's violated. But unbounded regions are tricky anyway. What one would really like to have is bounded regions, essentially double cones. And for double cones, this is not anything. And what we know, the only thing we know, is that weak causal completeness holds for space-like separated double cones. The philosophical conclusion, if I may call it a philosophical conclusion, is that these space-like correlations, although, as I have argued, are very endemic in quantum field theory, they are everywhere, still do not provide confirming evidence in favor of the rejection of the common cause principle. They cannot be regarded at this point as disconfirming evidence for the common cause principle, not even if the common causes are required to be local. But it's not known whether properly localized common causes do exist. Here's the definition of local primitive causality. Remember when I listed the axioms for algebraic quantum field theory, I mentioned in red local primitive causality. It's not part of the standard definition of the standard axioms. There are quantum field theories which do not satisfy it, but typically it is satisfied. This is the condition, which is an expression of the hyperbolic character of the time equation. But the formal expression of it is that the algebra, which is associated to the causal completion of a region V, is equal to the algebra which is associated with the region. So the way to imagine this is that if you have, say, a region like this, then the algebra which is associated with this one is the same as the one which is associated with the causal completion of it, which would be a double cone. So this is the double cone. This is X, this is Y, and this is the algebra which is associated with the double cone. And the local primitive causality condition says that the algebra AV is supposed to be equal to the algebra A associated with the double cone. Okay? So everything that that happens here determines, or everything which is observable here determines what can be observed in the causally completed region. Okay? This is strong enough, sufficient enough to define what's going on in a slightly, possibly slightly larger region. And that's the content of the local primitive causality condition. Here's an equivalent formulation of it, of what it means for a region to be causally complete. Okay, so if this condition holds, then the common cause principle can be shown to hold in quantum. Now, the problem whether the common cause principle holds without the adjective we has been around for quite a while. And there was an idea, and it's open. And there was an idea of why not trying to see what the status of the principle is in lattice quantum field theory, discrete quantum field theory, where computation is a bit more accessible because it's more explicitly, I mean, the algebras there, as we will see in a second, are finite dimensional. They're more amenable for computation. So two physicists, one of the students of mine, had embarked on investigating the status of this common cause principle in lattice quantum field theory. So let me just tell you what the situation is, what they have found. First, a few words about lattice quantum field theory in 2 dimensions. The discrete 1 plus 1 dimensional Minkowski space-time is just a subset of the discrete points of the 1 plus 1 dimensional standard Minkowski space, with time coordinates and space coordinates which have this form. And the time coordinate must be of this form where n is an integer. So if it is a half integer, the time coordinate is a half integer, then the space coordinate must be an integer. And if the time coordinate is an integer, then then the space coordinate must be a half integer. That's the idea. You should imagine a lattice. Imagine the 2-dimensional Minkowski space-time, and you imagine a lattice on it, a standard lattice, which you somehow rotate by 45 degrees. That's what the discrete version of it is, okay? With the space-time structure which is inherited from the 1-dimensional Minkowski space-time. There will be a picture in a second, and you will see what's going on more precisely. You can define double cones in that discrete space-time. Namely, you do the standard double cones and you intersect it in the discrete points. And then you also can define minimal double cones, which it does make sense to talk about points which have minimal distance in that space-time. And here's an example of what the minimal double cones in the discrete space-time would be. If you have 2 points, x and y, they have this form of the coordinates. And if ny is mx plus 1, then y is the future light cone of x, the unit time distance. And then the double cone determined by these 2 points, x and y, have 2 points. Okay. And this is a minimal double cone because the distance between the elements is minimal. Here's the picture perhaps that talks, that shows what's going on. So here's space, here's time. These are the points. As I said, it's just a rotated lattice in the 2-dimensional plane. And here are the points which are parts of the discrete space-time. This is 1 over half, this is 1 over half, 1 over 2, this is 1/2, 1/2. So a point which has this point has a half integer time coordinate and an integer space coordinate. This again half integer time coordinate and integer space coordinate and all the rest. And if you have 2 points here, x and y, this is the double cone. The red dots signify the double cone defined by x and y. Of course, y is in the future light cone of x. You take the backward light cone, the backward light cone, forward light cone, and the intersection of it is these 2 points. And these are the minimal double cones. Very straightforward. And if you have the minimal double cones, then you can associate finite dimensional algebras with the double cones in such a way that you obtain a discretized version of the net, which has all the features which correspond to the features, to the axioms of the full-fledged quantum field theory, namely isotony holds for the net, the closure of the double cone algebras defines the quasi-local algebra. It will be a specific quasi-local algebra, uniform and hyperfinite. It has an increasing set, an increasing sequence of finite dimensional full matrix algebras. Einstein locality, local commutativity holds, and there is a representation of the unit space and time translations, and local primitive causality also holds for the network. I'm not telling you how this can be done. This can be done. It's standard how you associate a matrix algebra to the minimal double cause so that these features are satisfied. The point is just that you have a discretized version of the algebraic quantum field theory in 1+1 dimension. And of course, in that set, the space-like correlation, the notion of common cause, the weak and strong locality of the common cause, all make sense, just like they make sense in the full-fledged version of quantum field theory. And then you can define the compliance of the discrete quantum field theory with the common cause principle, respectively in the weak and strong senses. So you can essentially, what you can do is you can translate the situation and the concept, the notions in the full-fledged quantum field theory into the two-dimensional, 1+1 dimensional discrete quantum theory. And you can ask the same questions with the hope of being able to show something which you were not able to show in the general case. Okay? So the question is what the status of the common cause principle is then in this discrete quantum field theory. This is just to recall the notion of localizability of the common cause. I'm skipping this because I've explained it. So, does the weak and strong and without injective common cause principles hold in that theory? That's the question. And here's a proposition which is relatively recent in Conditions of Physics 2010. The weak common cause principle fails in discrete quantum field theory. Okay, so remember that the weak common cause principle did hold in the general case. They have shown that it fails in the discrete version. And as a consequence, the common cause principle also fails, and the strong common cause principle also fails because the weak is really weak. It is surprising. To some extent, this is surprising because, as I said, the standard quantum field theory does satisfy the weak common cause principle. Why should the discrete not do so? You would not expect a causally different behavior in the discrete case. Remember, the intuition was, the original motivation for such an investigation was the hope that in the discrete case we have a better handle on the algebras and we might be able to say more, prove more than we could in the general case. And this intuition proves to be incorrect in some sense. On the other hand, I don't think this is very surprising in view of some of the results which I presented you. Namely, the local algebras in lattice quantum field theory are isomorphic to full matrix algebras, as I said. And therefore, the quantum probability theory, which is defined by such algebras, are measured theoretically not purely non-atomic. And the general results on common cause completeness in non-classical probability spaces show that measured theoretic non-atomicity is essentially equivalent to common cause completeness. So what you would expect is that certain correlations in that discrete version do not have a common cause within these non-atomic structures at all, irrespective of localizability. Remember that in the general case, there were common causes as a consequence of the purely non-atomic feature of the probability theory, but we just were not able to localize them properly. In this discrete case, there are no such common causes at all, irrespective of localizability or not. And indeed, if you have a look at the proof of that proposition, then you see that the proof is not the failure of the weak common cause principle is not that there are common causes which cannot be weakly localized. The situation is that there are no common causes at all whatsoever. Okay? Locality is in that sense irrelevant in that framework. So What are the options in view of this failure of the common cause principle in discrete field theory? Well, you can say that one should disregard the failure as physically irrelevant because it's just a result of the lattice model's peculiar feature that if it's too coarse, it's measured theoretically discrete. And then you might want to say that in the continuum limit, this artifact disappears. Now, these are very new results. I don't know what to think about them. Really, it would be interesting to see if there is some evidence for this hope in the second point here. I'm not sure, but certainly I don't see any evidence for this. Another option is that you might want to think about the notion of common cause again, and you might want to weaken it in such a way, in a disciplined way, that the measure theoretic discreteness of the quantum probability space is no longer an obstacle to obtain common causes. And this is possible. How would you weaken the notion of common cause? Well, there are two possible ways. One is to replace the common cause by a common cause system, and the other way is to abandon the requirement that the common cause events are compatible with the correlated events, that they are from the same distributive sublattice. I mentioned this to you in the beginning, emphasized that it's part of the definition that they are compatible with A and B, the common causes, and you might want to abandon that requirement. So these are two possible ways of, possibly not the only possible ways, but two possible ways of weakening the notion. Now, option one, what can be done, leads to new definitions and problems, of which many are open, namely going to the common cause system rather than the common cause. But it doesn't have. In the paper which I referred to previously in connection with this proposition, it is shown that the lattice does not allow common cause systems either. So there is no system due to the discreteness of the lattice. The other option does have, namely if you weaken the notion of common cause by abandoning the requirement that it's compatible with the correlation, then something can be done. I skipped the common cause system. Issue, which will not fit here. It's interesting in its own right, but I moved to the non-commuting common cause system definition. So here is the definition, which is a definition of common cause system, and which also abandons the idea, the requirement that the common causes in the system should commute with the elements which are correlated. So suppose you have a partition in a quantum probability space, and this partition is called a non-commuting, or possibly non-commuting, Reichenbach common cause system for the compatible events. If for all elements in the partition we have the following: first of all, that there is clear of the correlation, and second, that they have they satisfy an analog of the statistical relevance condition. But now, instead of the classical conditionalization, you have the non-classical conditionalization, the Lüder's rule. Okay? Since CK is now not assumed to commute with A and B, you conditionalize with respect to the quantum conditionalizing rule, that's the Lüder's rule. Okay? So, you have here a substantial weakening of the notion of the common cause. First, because we allow for common cause system, many elements in the partition, not just C and C orthogonal, but a partition which can have a larger cardinality. And you also replace the classical conditionalization with the quantum conditionalization. And then you call this a non-commuting Reichenbachian common cause system. I would like to mention that you also might want to drop this second condition, weaken the notion of common cause even further by dropping this condition completely. If that's done, then you call this common cause system a non-Reichian barrier common cause system. And with obvious specification of locality, you can then define the non-commutative weak common cause system principle, the non-commutative common cause system principle, and the non-commutative strong common cause system principle, and you can ask the same questions as before for this new notion of common cause system. And then the problem is what the status of these common cause systems principles are in quantum field theory. This is very new. Hardly anything has been done in connection with this. It is essentially open. The only known result is in a very recent paper which has been submitted. I don't know if it has been available in from the preprint, but the claim is that the non-commutative weak common cause principle holds in lattice quantum field theory. That is to say, allowing for the non-commutativity of the common cause system, the elements in the partition, compensates for the discreteness of the lattice. So here now you can show that there are weakly localized common cause systems for the correlations, discrete 1 plus 1 quantum field theory. Nothing is known in higher dimension, and nothing is known for the not weak common cause system. So again, nothing is known about the status of the common cause principle, not in the weak sense, in the proper sense. Again, proper meaning that the common causes are localized in the intersection, that you want them to be. Nothing is known about this problem. It's been around for 15 to 20 years, I don't know. First time it was formulated, I believe, it was in my paper 1998 in Foundations of Physics. And the problem is open. Now, given this openness of the problem, you start speculating. Why don't we know what the situation is? And here's a logical possibility, which is an intriguing possibility. Namely, you recognize that quantum field theory is specified by axioms. And the causal completeness is a property of quantum field theory that holds or doesn't hold as a consequence of the axioms. But it is a logically possible option that the axioms are not strong enough to determine the question. So the axioms are just too weak to give an answer to the question whether properly localized common causes exist or not. Now, this is a logical possibility, and it's an intriguing one. If you formulate this, if this idea happens to you, as it has happened to me anyway, then you might want to conjecture that indeed this is the case, that this is the claim of the causal independence in that sense is an independent claim. It's not provable, but its negation is not provable either. Now, to prove this conjecture, you, of course, how do you prove independence of a statement of the axioms? Well, by providing a model in which the statement is true and providing a model of the axioms in which the statement is false. Now, to do that seems almost beyond hope, at least for me. But this is what could be in principle done, and it seems to be very difficult. I think what one should do is perhaps to have a look at the existing models of the axioms and have a look at, in those particular models, what the situation is. And this has not been done yet. So there's a lot to be done still. If you're interested, I hope I excited you a little bit about this. And here is a summary of what I've said today. First, the common cause principle states that probabilistic correlations have a common cause type explanation if they are not results of a direct causal link between the correlated events. That's the general principle. And since we have seen in the previous lecture, local algebraic relativistic quantum field theory predicts correlations between space-like separated observables. the causal completeness of that theory would entail, should entail, the existence in field theory of properly localized common causes of such space-like correlations. And at present, it is an open problem whether such common causes exist, which are localized in the intersection of the vector-like modes of the space-like separated observables. Only common causes localized in the union of the vector-like modes are known to exist. And a very speculative idea, it might be undecidable on the basis of the axioms of quantitative theory. Common causes possess stronger locality properties. It would be very interesting, I think, if this turned out to be the case. And with this, I think I'm just on time, and I finish, and thank you very much for endurance and for your attention again, and see you tomorrow if you feel like. Thank you.
Ask any question?
Sure. Well, you could ask any question during the lecture as you have done. So, but if you feel,
I have one. This is a very beautiful theory, but it's quite abstract. And in the field of quantum information, there are a lot of work about entanglement, which relates to non-locality and solidity. And from such a point of view, this common cause is always, in what sense, the help to understand the entanglement. For example, can we understand correlation existing entanglement can be explained by some common cause or something?
I think this is a very interesting issue. I don't have a satisfactory answer to that. Let me say in the beginning, because what I have described here is the explanation of correlation, no matter whether the correlation is coming from entanglement or not. Okay, so here the common cause principle is about correlation, ordinary correlation between two events, A and B. And from the perspective of the principler, it doesn't matter, or it doesn't play any role anyway, whether this correlation is the consequence of an entangled state or it's just a classical correlation. So the common cause is insensitive to that very crucial difference. So what you're asking is really an intriguing question. Is there a notion of explanation in terms of common cause which would not be insensitive to the origin of the correlation? I think that's a very interesting question, and I don't have an answer to that. What would be the notion of explanation in a common cause type explanation of correlations that are results of entanglement? Or to put it differently, what would be the common cause type explanation of entanglement itself? Okay, I think that's an intriguing issue, and I don't know the answer. I don't know the answer to that. I haven't seen any attempt, although I think it would be conceptually very interesting, because of course entanglement is crucial, and the correlations I have talked about here in this quantum field theory context do emerge from entangled states. We have seen that there are consequences that we didn't see, but I made it more or less clear that it is a consequence of the violation of Bell's inequality in quantum state theory. That is to say, it's an entanglement phenomenon. Correlations are coming from that, but the notion of common cause is not, I would say, it's not sophisticated enough to explain the origin of the correlation. So that's an intriguing issue.
So, if I well understood, is there a notion of classical correlation versus non-local correlations in quantum theory, like there is in
standard interspace communication from?
Well, local, there is, in this quantum field theory framework, there is a difference because the correlation here is always, since all the observables carry with themselves a label as to where they are in space-time, because all the local observables coming from an algebra which is associated with a particular space-time region, all the observables carry a label with them very openly. I'm from this region, okay? So if you display a correlation between local observables, that correlation will be local in that sense. You know the locality relations of the correlated entities. So, so there is a particular type of local correlations, local in that sense, which is not local in which you use the term local. There's a particular type of local correlation, namely the correlation between space-like separated entities, which is very intriguing, which is very much crying out for explanation.
So maybe I can reformulate to see whether I understood an outcome. So the common cause can be whatever. I mean, we don't have any distinction between a classical common cause or a quantum common cause. Like, you know, in the Bell experiment, you have common source, it sends entangled particles, but it could also send classical random variables, like hidden variables. So here the common cause would be whatever.
Well, not whatever, perhaps. I mean, here you have a theory which specifies, in principle, everything there is, namely the observables there on the space-time. Okay? And we are asking whether there is a common cause type observable somewhere specified by the theory. So it's not just any. In that sense, in the sense of being part of the theory, which is quantum field theory, it is a quantum common cause. Okay. So it's not just any. It's when I'm asking whether the theory is causally complete, I'm asking whether there are observables specified by that very much quantum theory, whether such entities exist. In that sense, they are not classical. The other reply in that connection is that, of course, when you relax the notion of common cause by allowing the thing to be non-commuting with the correlated entities, you explicitly allow for the quantum to influence the notion, because non-commutativity is a typically quantum phenomenon. So you might want to even say that it really, the truly non-classical common cause is the one which does not commute with the correlated entities. Yes.
You're now talking about algebraic theory. But this is one of the formalists for quantum probability. And also the usual quantum mechanics is also another theory for non-quantum probability. And even the finite dimensional Hilbert spaces describes such kind of entanglement.
Yes.
And then they describe the experiment just using only the two-dimensional Hilbert space and tensor product.
Yes.
But this is one formalism for quantum probability theory, and then you can investigate such kind of cause completeness other than quantum field theory.
Yes.
In more general context of the generalized probability theory. In that sense, you can you say that in ordinary quantum mechanics, in the sense of it is incomplete. However, if you describe the same physical phenomena inside the algebraic calculus in some way, then you can make that theory to be complete. In that sense, your algebraic quantum theory is more complete theory to describe quantum probability. Can you do such kind of explanation of the superiority of the field theory compared with the ordinary quantum mechanics?
Well, the algebraic version is the advantage of the field theory approach is that the spatio-temporal conditions are very explicit there. So when you're saying for, say, ordinary quantum mechanics that the observables are m times m2 times m2 two-dimensional EPR situation, okay? And then you say that this is space-like from this, then this is a very informal and not operationalized claim. It's just intuitively there, because of course, if you have an entangled state and you measure on them here and there, that's the model. It is not part of this model explicitly that thing is somewhere, which is space-like from that thing, which is also somewhere. So this spatio-temporal intuition, which is very much important in connection with the standard EPR kind of situation, is explicitly present in the quantum field theory framework. Again, because observables carry a label with them. I'm here and there. So while I would not say that problems associated with that situation can be solved in the field theoretical framework, but I think the field theoretical framework is the proper approach towards the problem of whether causal explanations are always possible, which satisfy our intuition about spatio-temporal causality, because the spatio-temporal causality intuition is explicitly expressed in the formalism in that theory.
Excuse me.
Yes.
In spite of your claiming the explicit labeling of the space-time structure, in view of the isomorphisms among all the different local subalgebras, seems to show the, how to say, absence of such explicit labeling in spite of our formulation. So for me, such a way of labeling is still insufficient.
Okay, good. You are referring to the limitations of the kind of field theory I've talked about. Namely, it's on flat Minkowski space-time. There is an isomorphism of the space-time, as you say, and that has limitations. You're right. So, to which I would reply the following: raise the same type of question, if you can, on a quantum field theory which is on a curved space-time. Now, we do know that there are problems with that, of course, but that would be the way to go. If you are unhappy, as I think you should be unhappy about the symmetry, too strong symmetry assumptions in this kind of field theory, then the way to go to make it better, to make the treatment better, is to consider quantum field theories which are more realistic. And that would be the way to go.
I do not like to go to the direction of curved space-time quantum field theory, but my claim is just mutual inclusion relations among different isomorphic local subalgebras must be regarded as the most important piece of information regarding space-time patterns. And this can be somehow compared with our familiar observation about Hilbert space structures. If two Hilbert spaces have the same dimensionality, they are very isomorphic as Hilbert space.
Yes.
And the isomorphisms among different local subalgebras tend to show the similar features. For instance, in the context of subfactor inclusions, in this context too, we encounter the isomorphic subalgebras. But the inclusion relations tells us their structural feature.
Yes, that's true. So, okay, I have not talked about this, not emphasized this aspect, but if you remember, there was a slide here about the type of local algebras. It's a result of quantum field theory to show that the cone algebras, under certain conditions, the double cone algebras are all type 3, and I have not stated this, but actually more is true, that they are not just type 3, but that they are type 3, 1, and they are hyperfinite as well. And there's only one type of hyperfinite factor in every category, so there's only, essentially confirming your point, all the double cone algebras are the same, okay, isomorphic. This is what you have emphasized. This is true. So the real content, the content of the theory is, this was your claim and this is the standard view, is not just in the algebras themselves, but in how the algebras are related to each other in the net. Okay, that is completely true, and I have not emphasized that. There's an awful lot which I have not emphasized, and that is true. And it has far-reaching consequences and features as well. How this inclusion is in one of them. One is that the split inclusion property, namely that if you have a, okay, there's more to say here. There would be a whole course to give on this.
Because of time, maybe
Okay, efficiency.
please continue the discussion in a time more.
Okay, good.
And I have an announcement about our schedule. Tomorrow morning we start 10:30. This and this is a final lecture of this course. And on Saturday and tomorrow afternoon we couldn't keep this room. However, we have the smaller next room. So if you want to use your own work, you can use the next room. And on Saturday, we are planning to have the workshop. And now we're planning to have two talks. And if anyone wants to give a talk on Saturday, please let me know. And this is in the afternoon of Saturday, and start at 1:30, the same as today and yesterday.
In this room?
This room.
Is it in Japanese or not?
In English.
In English?
Yes.
Because I asked Francesco about this, and he couldn't confirm that it would be in English, so I was just wondering. So
yes.
Saturday afternoon, which day is today, by the way?
Saturday is 25th.
25th, and today is the 23rd?
Yeah, day after tomorrow. Tomorrow is Friday, and Saturday
Okay.
day after tomorrow.
Yeah, okay, so
Tomorrow is we have the in the morning, start at 10:30.
tomorrow 10:30 I'm speaking,
And Saturday we have the workshop in the afternoon, start at
at 1:30 here.
Yeah. And on Sunday we are just under planning. We may have discussion in the morning or Sunday.
Good.
But not yet. So
And
we
we-
announce tomorrow or
Good.
on Saturday.
Good. So I see you then tomorrow at 10:30, those of you who are still interested in what I have to say.
and in the afternoon, the workshop. At 1:30, right?
Yes, on Saturday.
I'm sorry, tomorrow afternoon?
Tomorrow after we have no organized.
Yes, and we have to
but we can gather privately and discuss or work your homework. We keep the next room. Lecture room 2.
Sorry?
We keep the lecture room 2 tomorrow afternoon.
Yes, I understand.
Tomorrow morning we can use it. And
Good.
your lecture here.
Yes, okay, good.
Okay.
Thank you.
Let's meet once again.
Thank you.